Okay, hello everyone. So this session is about securing private keys in edge data center using hardware trusted execution environments. And my name is Manish Dave. I am a principal engineer in Intel in the data center and AI group, primarily focused on security solution for our cloud customers. Okay, so just want to step back and, in general, data protection is really, critical for any business. And encryption is really a very effective and primary control that everyone deploys, right? But however, the strength of your control, which is using encryption, it depends on how well you can protect your private keys. And the statement I'm making here is, the software-based key protection is not sufficient. Of course, we are using it today, and there's a lot of mitigating controls we put in, but it is not sufficient, and especially so for more growing number of edge data centers. The reason I say that is more often than not, you will introduce third parties in co-location and things like that who will have access to your physical and sometimes even administrative control, administrative access to the server, even though it's only for provisioning. So that introduces like an additional, sort of risk that you need to mitigate. But this is still true for any, compute node where you're processing or encrypting, and then you need to protect the private keys. Now, you may ask, like, okay, so there have been solutions in this space, right? The hardware security module being one. It's a tamper-proof, FIPS compliant, hardware modules that you can, deploy. However, it's a good solution for your centralized PKI infrastructure and such, where you are generating the keys and, signing the key material and all that. But doing this for hundreds, if not thousands or tens of thousands of nodes, is probably cost prohibitive, and this is why we're not seeing, many people do this on every compute node. The other solution which I've seen, in the industry, you're also probably familiar. This is SecuriTrack. Most of you already, familiar with this. Is this the TPM, can be used to do this type of, secret, storing the secret on the platform. However, if you think about it, when you're using the keys, right, when the application is actually consuming the keys, it doesn't really provide the full protection, while it is in the memory. It's a good solution to have, and like defense in depth for security, you do need to do things like that, but it doesn't provide the full coverage. And on top of that, there are some deployment challenges. If you have done work with TPM, there might be deployment challenges depending on how well it works with virtualization, multi-tenancy, and so on and so forth. Okay, so that's sort of the problem area that I'm discussing today. But before we jump into the solution to this space or this problem that we defined, I want to step back and talk a little bit about the hardware trusted execution environment. In this case, we are using is the Intel Software Guard Extension, SGX. So what is SGX? To be honest, it's not doing justice to try to explain all the details, in a less than 20 minutes, plus also explain the use case. So in that interest of time, I will just stick to the main properties of SGX. And there's a lot of reference material which are there and things like that, but I can also answer questions. But the top three properties. So on the left, you see the typical sort of simplified platform system diagram. You have a hardware, you have the Intel processor which is supporting the SGX extensions. And then you have something like a privileged software like virtual machine manager. You may or may not be using virtualization, but some kind of a privileged software operating system. You might have another layer for your container runtime or other things which I'm not shown here. But at the end of the day, you will have some applications running on top of it. So what SGX does is first property. It removes all this privileged software that you see, right? The OS, VMM, SMM, and such, the device drivers, all those things, and also additional unprivileged software running on the same platform. It removes that from the trust boundary. What I mean by that is there is a hardware-based access control which is enforced so that region in the memory, which is shown here with this circle here, is protected and isolated using a hardware-based access control. So that's the first property, right? So it removes everything else which is higher privilege or even same privilege on the same application running on the platform itself. The second one is it encrypts the memory. Now, this memory encryption is really, it has twofold, right? One is like it's encrypting the memory, to make it opaque to everything else running on the same platform. But more importantly, also encrypting so that it can protect against, some of this, memory bus snooping, cold boot attacks, and such. So, you may or may not have to worry about this type of things if you're physically securing your server. But in cases where, somebody else has physical access, you could do like a freeze spray and remove the access and, sort of retrieve your secrets, so to speak, like the private keys and such. And then finally, the remote-based attestation on the hardware. So one of the properties of SGX is that you will, be able to remotely attest. And I have a picture which shows the flow, but you'll be able to remotely attest, and then only then, after you have done the attestation authorization of the platform and make sure that everything is as it's supposed to be, only then you're able to provision the secret into the enclave or the trusted execution environment. So with that background, let's talk about okay, so why do we need something like this in the first place? And again, I will talk in general concept, but think about the key protection use case. Okay, so in general, a system consists of, operating system, some privilege, and then some applications and the things running in the user space. Now, the typical sort of access control implemented is, the OS, is able to, OS or the lower level, the protected mode protects OS from the applications, but not the other way around. And also, it doesn't protect the application from itself. Now, what this means is architecturally, if you didn't have, any kind of isolation for the application, if something else on that platform, not your own app, in this case, think about the key protection, but maybe it's not your crypto library or whatever you're using to generate and use the keys. But something else might get compromised, which means that it can then go in from the back door through the privilege level, do the escalation, and then do the attack on your application. So just think about it now. This is just one scenario. Something else got compromised in the user land, and then it went through and then did the escalation and came back. But what about things like when your operating system drivers have vulnerabilities, some backdoor, something else which might be still there, right? Sorry about that. Okay, so this is where the SGX comes in. So the same picture here with that enclave, the protected memory that we talked about. So this is kind of like your initial sort of way to show like where the application secrets are kept. And then it's hardware isolation and encryption like I talked about, and it cannot be accessed from the same channel that we talked about before. So basically, that's sort of the architectural reason to have an isolation, a hardware-based isolation within the user space, application space, dedicated to the memory. So the other way to think about it is, what is my attack surface? Again, think about, like your key protection or any other application which has secrets that you need to protect. So now think about a traditional platform. You have to harden, and you will harden, and I think it's a good idea to harden, but you have to depend. Your attack surface is pretty big. Like your virtual machine manager, might be compromised. Somebody internal might have access, privilege level. So basically, your application is vulnerable to all of those attack surface, right? With the hardware trusted execution environment like SGX, the attack surface, you see the dotted sort of boxes, just reduces to those levels. Well, doesn't mean that you would not or should not harden your rest of the platform. The point is, you have an additional layer of hardware-based access control, which is then reducing sort of your trust within that small application region. And of course, the part of the hardware which is enforcing that, which is using the encryption that I talked about in the hardware, and then the access control which is happening in the hardware. So that's sort of the rationale behind having a region of memory at the application layer, which is protected, with the hardware. So hopefully that gives you like a good overview. Now let's go back to the use case. So the use case again is the private key protection using a hardware TE, in this case the SGX. Hardware-wise, you will need, basically an Intel processor. So I mentioned here Ice Lake Xeon Scalable because that's the Xeon Scalable processor. But any current or future platform supporting SGX should be sufficient. Now let's talk about software, because next of the couple slides are going to talk about what actually software we're needing for this solution. So first is your existing application. We're going to use something like Nginx just as a reference. It doesn't mean that this only works for Nginx. This will work with any of the code that you have. It might be your sidecar, it might be your service mesh, it might be your own microservice, it might be your own developed application. So just that application which is consuming and using the libraries, which is the next thing, right? The crypto library itself. So again, in my reference implementation, we are using OpenSSL as an example, but this could be any other crypto library, like Boring SSL or whatever else that you're using or developed yourself. The third and the fourth are the SGX specific parts, right? So the first two are really, they need to have the PKCS11, they are the crypto library and the application itself. The third part is the SGX enabling. So the point here I want to make, which is the note I made here, one over here, is this is just enabling so that the extensions work, so the software can access it. So basically, it doesn't mean it's really used for resource allocation management and things like that. It is not in the trust boundary, right? It is just, think of it like, it is enabling these instructions to be used at the application layer. It is enabling the OS to be aware that there's SGX, enabled hardware. And then the final thing, this is really the meat of what we're talking about here. Basically, this is the modified soft HSM project. There's a link over here on that, which is the open GitHub project that we have. Basically, it's a modified software HSM project, which is using SGX. So it's using SGX instructions, and it has already been modified, so it can cater to all your private key operations running inside the enclave. So that's sort of the main the code change that we have done. Okay, so now let's step back and think about the attack scenario and how the whole flow will work, right? So first, step 0 is your platform comes up. It will have the SGX enabled and so on and so forth, right? But then, think of it like in our reference implementation, we have really two servers. And we realize that in production environment, it's not going to be the case, right? There'll be hundreds, if thousands of compute nodes, and there'll probably be a cluster of backend servers, which are the key servers and doing the verification, all that. But think about, there's two sort of entities, right? The compute node and then the backend server. So the first step which will happen is on the compute node, there are some, as part of the SGX drivers and things like that, there's some infrastructure enclaves, we call them. This is really the software which is doing the measurement of the CPU, the TCB, the trusted compute base, the identity and integrity of the key protection enclave. Remember the enclave that I talked about, the crypto toolkit-based enclave, right? So it's doing all of that, and then creating sort of a hash along with the session public key. Now, this session public key, to be noted, is nothing to do with what Nginx is going to use. This is just to communicate a mutual TLS session with the backend server so it can retrieve the keys, okay? So this is step 1. So it will create that whole code, the whole attestation code, and then it will put it in, along with the hash of the public key, it will just send it to the server. So the next thing what will happen is the server, because it has the data, it will validate, I'll just put it on the side, sorry about that. It will validate, it will verify, I would say, the attestation code and everything, because it already knows, because there is some initial steps which have happened whenever the server was provisioned, it has the right keys and everything, so it knows how to validate whatever came in from the CPU and other things, right? So once it's done that, then it will provision the keys. Now, these keys, in our simple example, are provisioned locally, right? But in production environment, they'll be provisioned from some network HSM, or there might be some central HSM, or you might generate it your own, whatever you are doing, right? But these are the actual keys which get wrapped and then sent back to the compute node. And then the compute node is going to just receive them and then unwrap and then put it in sound. At that point, no more exposure for the private key. So once this, the first 1, 2, 3 have happened, all the stuff happens then inside the enclave. So then the protection that we talked about with those boxes inside of the enclave, those then come into picture. So after this, any connection from the Nginx, or in our case Nginx, but any other application which needs to do the processing of a private key operation, it will send the request to this enclave, and then all of that gets executed inside the enclave, which is this isolated environment, right? And then, of course, the application doesn't need to do that. Only requirement, the way we have built this, again, it's a reference implementation, is it will support the PKCS11 API, right? So, and we have implemented most of the, I mean, I can quickly show the screen on, functionally, it's fully functional in the sense it may not have all the different algorithms that you would need and things like that, but it is enough algorithms and support that it can handle most of the private key operations. Okay, so with that, I want to jump into this sort of like a component / architecture picture, right? So you see on the top is the application that I've been talking about, Nginx. This could be anything else. Then you have the library, which is the OpenSSL library. And then you have the PKCS11 sort of interface. And then the provider, which is then interfacing. And this part, if you can see my mouse pointer here, is where the enclave is. So you can see this kind of like, we have like this border of that. So this is the only part that needs to get trusted. And this is the code which will be put inside the enclave. So you can see like all these operations go into this, right? As far as this is concerned, this is just the infrastructure software that I talked about when SGX gets enabled. The role of this one is to do the attestation that I talked about, the initial provisioning of the keys and pushing it inside the enclave. So that's this part. And this is my simplified one server. The data center access, attestation primitive is our name for the attestation library. So we just put that all and the key services, again, to simplify the reference implementation on a single node. Again, in real environment, that will not be the case, right? But we have all of that here. So, if you see like, the step number 1, 2, 3, like I explained before, first is, your SGX enclaves get launched, the measurement happens, it will go, get verified, and then the key gets provisioned, and then the application from there on requests everything which runs inside of the enclave as far as the private key operations are concerned. So that's sort of the summary of the whole reference architecture. And just the sort of note here is, even though this color says open source, which basically means that you don't need to modify this part, this is the Intel reference implementation, but it's still open source. It's not that it's not open source, so sorry for the confusion if it might have caused, but it's a reference implementation, but it's open source. And I have the links in the next slide. And then, of course, we talk about the enclave. Okay, and then I forgot the box on the bottom, which is, of course, your platform and the operating system running the right versions of the driver, everything else, and things like that. Okay, so to summarize, we kind of like, this is like a short talk and, really didn't go too much into the SGX. We focus mainly on the use case. We focus on the properties of why something like SGX makes sense to, protect, private keys and something like that, which is more critical than, trying to protect the whole platform and run everything inside of it. So first, from a scalability perspective, the solution will scale because unlike some of the other examples we talked about, like physical HSM or other things, it's really software at this point. It's just any number of compute node, things like that. You can just containerize it and you can just run it at that point and things like that. So the scale, horizontal scale, and everything else will work to hundreds, if thousands of nodes. The second is the performance. Now, for the performance, there are two areas, right? So there is a key operations, which, of course, you can optimize to run inside the enclave, which is what we're doing as like a part of being Intel. We're doing all of that. But think about it. That's just a private key operation. Once the session keys are created and the Nginx is talking to the like your cache layer, or maybe it's directly connecting to your origin server, whatever it's doing. That part is not, so it's not in the data path, right, basically. But yeah, the private key operations, depending on how many times you renew it and things like that, that will have some overhead. Our current measurement is mostly single digit and things like that. But yeah, definitely, because you're securing it, running it with this all hardware and environment, it's going to have some overhead, but not the data path. And then finally, the security, which is the reason we are advocating something like this, because it removes most of these attack vectors we talked about versus running these private key operations in the clear. Because once you run it in the clear, there is a lot of other risk which come into play, right? So once you're running these private key operations in the enclave, they are overcome, so to speak, right? And then sort of a word of caution, like security, I said, is defense in depth. There's always things like you need to harden, you need to make sure you're doing right things and doing the right testing of the software and things like that. So in this case, following the development cycle, remember the application itself that you're securing, that's still in your trust boundary. So if there is something wrong there, you can still expose, right? So just doing all those testing and things like that. And here's the kind of the call to action / all the links. So this is a reference implementation. It's very nicely documented here in the bottom 2 PDFs. There's code. The whole code that I talked about is all available. These are the links to all the different sort of, the components that I shared in the previous slide. Those components are all on GitHub and available. And we would welcome contributions, right? Especially when you're doing something in production, you might see, oh, this is not there or not there. We'll love the contribution or even raise issues for us. So that's pretty much sort of the conclusion. And then, no work is done by yourself. So these are the other people. Kapil led the reference architecture development, the document I shared and things like that. And the rest of the team here, helped build and validate it. So I'd like to thank them. And I think that's it. I think that's all I had. Apologize for the pop-up here. I don't know where it came from, but. So I think we can take questions, if there are any. Okay. If not, then thank you so much for the time.